Okay, Linus, welcome.
Hi,
welcome to the stage. Nice to see you in Kiev.
Nice. Thank you. We had some problem with the microphone. How is my hair looking? Is it like horrible? It's good. Okay, thank you. So there's my clicker. That's good. It's nice to be here. Good morning. Dobro utro. Juregelt kivanok. Whatever language you're talking. Good morning. I made a bunch of presentation slides and a talk here for about pin control and GPIO, and it's going to be complicated. So we're going to do hard stuff. I've done this talk in an earlier incarnation at the Embedded Linux conference, but now it's much more rewritten. We are focusing on GPIO and pin control at the same time. We're going to go in and talk about what the different things are, which piece fits where, and so on. And we can start from the beginning. It's a good place to start. What input-output or GPIO is really all about is signals. So the acronym reads out, is there a laser on this one? Maybe there is. No, there should be a laser. Could be this one. Yeah, look, this is this. Ah, it's it's green. Oh, why it's green? I can't see it. All right, what is GPIO? It's the general purpose input-output. Yeah, this thing is almost, no, it's better. So, general purpose, not specific purpose. And each of these general purpose input-outputs we refer to as a line, and it can be deasserted, or zero, or asserted. And this is, of course, an electromagnetic signal. It's a voltage. We are all familiar with voltages. So it has another important property is that edges, where it rises and falls. And if you do, say, Fourier analysis or Z transform or something like that, that's super interesting, this square shape, because it has very interesting mathematical properties and so on. In the Linux kernel and the designs I do, we don't care. That's for analog people to do all this kind of stuff, or signal processing people. They can do all interesting things with these curves. But for us, it's lines, and there are several of them. Here you see one. And we assume that this line is digital, so it has more or less just on-off properties. It is usually routed out through a specific physical pin on a package. Not always. There are exceptions to that. So the GPIO is just some output of some hardware where you can control it low or high in a generic manner. It's not there for a specific purpose. It's there for any purpose. And they can be in output, like here, I drive it, I say go high, go low, and so on with software, and it can be input. So I read it and see, is it high, is it low, what is it? And then I don't know, then it's more like I have to figure it out. And then another thing you will run into is edge detection. So we can detect these edges if we're running it as an input. It comes up here, it comes down there, and there are synchronous and asynchronous edge detection. The synchronous one has digital logic and a clock. The asynchronous one is an entirely event-based thing that is analog. And many GPIOs, for that reason, also are interrupt controllers, because you want an interrupt when you get an edge or an event on a line, like so. Let's talk about what it's used for. I will go into details about all these things. These are, I got a bit of panic last night when I arrived and was like making my rehearsal for the presentation. I felt like, yeah, no, I promised Sam to put this in and then I forgot it. So I put it in last night. These are all the things that we use GPIO for. the most exotic and everyday things are over here. It's automatic control. Those things you know about. There are power plants and factory lines and robotics and farming alarms, burglar alarms, heat alarms, whatever alarms, automotive. There were some automotive guys here. Spacecrafts, ventilation, whatever you do that is in automatic control or industrial control. Ultimately, pretty often comes down to controlling a relay or a line with some voltage that drives some electric thing that turns on a bell or a whistle or reads a contact on a door that sets off an alarm, that opens a door with an actuator, something like that. Those are the most mundane, profane applications of GPIO. There are lots of people who use GPIO for exactly this. They put them in small boxes in buildings, for example, and then they use a special serial protocol that can support longer lines than RS-232, and then they talk to them and control doors and ventilation, windows, and all kind of stuff. Factory lines, there are people running that. There is lots of GPIO and robotics and so on. Also maker communities over there. Makers do all kind of stuff with GPIO. Then what we have seen actually in the Linux kernel is not very much of that over there. That has always been done by some kind of hack in user space. What we have seen in the past, in the subsystems in the Linux kernel, have been all of these use cases you see here over on the right. First, a lot of housekeeping, like turning on and off LEDs, regulators, a power somewhere, detecting when somebody inserts an SD card into an SD slot on the board, random keys, just keyboards that are built up from GPIOs, tilt switches, reset. You can often find that there's a GPIO you can pull down in the system or pull up, and then it resets or powers down. So this kind of real low-level housekeeping, detecting if somebody inserts a headset plug. And then quite early on, and this was maybe real even before that, there was a bit banging of different buses. So if you take, say, two free lines, SD data clock and chip select. I say that's an SPI bus. But most people think maybe you need a special hardware to drive an SPI bus. You don't really. It's just a protocol on free concurrent lines. So SPI, I2C, MDIO that they use in network. You can do pulse width modulations, but be a bit careful with that because you probably need real-time patches for that to get right. You can read flash chips and so on. And since we support SPI over GPIO, so we can just take some pins on our system and turn them into an SPI bus, that means that we can solder them into an SD card or SPI, SD card or MMC card. And that means that there's a very simple way for if you have a BeagleBone or whatever to get a full gigabyte of storage, several gigabytes, terabytes, just by soldering free lines, instantiating a bitbank GPIO driver, and then running SPI on that. It's not going to be fast, but it's going to be big. So you can have lots of stories. I don't recommend that for industrial systems, but you can do that. For your hacks, you can always get some storage with just free lines of GPIO. So these are the use cases. This is what people are using it for mostly. In the Linux kernel, as I said, we had a bunch of abstractions for GPIO. The drivers are in that directory hierarchy. That's where I run around and manage and merge patches and so on. I do not do that on my own. Most developers are out there. So Andre is going to have a presentation on how to submit patches and so on. And he's actually second man in GPIO. So if you have questions about GPIO, you can just as well ask him. He will sometimes give a better answer than me as well. So we are several people out there doing this. I'm just some guy, some figurehead. And then, yeah, so if you're using GPIO inside the kernel, you just say like, yeah, if you're going to driver hardware. You include a driver. If you're going to use GPIO, you're a consumer. Driver consumer is pretty straightforward. There is an old header file. Don't use that. Just try to have this separation, that there's my driver, and there's my consumer, and there's an abstraction in between. We have worked very hard on this and tried to make it more and more abstract. So there are some reasons for that, and I will go into them. It's mainly to do with this. We had a problem in the ARM community that GPIO was introduced in the late 90s, and it was introduced on the assumption that, yeah, you have an embedded system and you have like 32 GPIO lines. Okay, that's nice. Let's construct something that enumerates them 0, 1, 2, up to 31, and we're done with it. We just send the number as a parameter and then switch that line back and forth. That's good. Should be good for everyone, right? No. So the problem is the world has, for embedded system, has grown, and also for laptops and everything. So now people put the GPIO on, not just on the main chip. They put it on expanders, on I2C, they put it on USB, they put it on PCI, they put it everywhere. So I get a bunch of chips coming up when I run my system. I get one GPIO chip here, and then a bit later I get another one, and then another one, and then another one. Okay, what about this number from 0 to 31? Yeah, I'm in hell, right? I just have to assign some base number like 64 or 128 and so on. And people started doing that with macro files and enumerators in their system and just compiling everything in at build time, and then added some dynamic support to choose a number a bit arbitrarily. We just have to get away from it. We had the same problem with interrupt numbers in Linux a long time, but we are slowly walking away from it. And the problem we have, or the big problem that you should really look out when you're designing an operating system, is to encode any such assumptions like there are only going to be 32 or something like that. That's just like any time you do that, just don't do it. We have to do something abstract. We have to have a GPIO chip, and there's an offset on the chip. So that's what we have now. And when we ask for a GPIO, we have to ask it through the device driver core with the GPIO, the get, I think is the main abstraction we use, and we get it from a hardware description like device tree, ACPI, or board files. You can use board files, but just keep it abstract. Don't hammer it down and say it's a certain number. And that refactoring has been going on for years, and it's going to go on for years and years again. I don't know if it will be finished when I retire. That complex the kernel is. But I'm trying to do it. Please help. So what we are using now are descriptors, and they are opaque cookies. It's just a pointer, and you get it from this consumer interface here when we use it as a user. The drivers, they get an offset from 0 to n on their controller, and we're creating the GPIO handle from there. If you need interrupts, you can convert these descriptors into interrupt line number, which is nice. If you have a generic use case that you want to do, like a LED or a switch or connector of some kind, then look in this file, drivers on GPIO, because there's a high probability that what you want to do, somebody else has already done. Like the bit banging things that I mentioned. Somebody has already done that. Use those drivers. Don't reinvent them. I've seen so many vendor kernels where people have reinvented the GPIO wheel so many times. Not just for kernel space, also for user space. They often have some like my fun in GPIO module where they just insert user space calls randomly into the kernel. But don't do that. I've created something for that. I'm going to present it right now, soon. This is it. So what people did in the past was, yeah, they used something called sysfs. Sysfs was very popular in the around the year 2000 as the next big thing from the Linux kernel. It's like a file value paradigm. There's one file, it has one value. So cleverly concluded that we create one file for this 0, 1, 2, up to 31 GPIOs, and we just write into that file, and we get sometimes create the second file that we write into, and so on. So everything was very file-oriented. That was the snake oil of the day that would save the world. It was an extremely bad idea. It should never have been merged. Unfortunately, the person who was maintaining GPIO subsystem at the time was David Brownell, and he died, physically died. So there was nobody there to take care of this problem or say no. Instead, it was merged through Andrew Morton's tree, because the principle we have, we can't hold back on development. We don't stop development in the kernel. We don't say to people, go away. We just like, okay, if nobody else says anything, your patch is going to get merged. And that's what happened. After a while, Grant likely took over the subsystem, but the damage was already done. And then I took it over, or I listed as co-maintainer for the GPIO subsystem, and then Grant sneakily just removed his name, so I was left alone with it. But now I've been taking care of it for a while. And I got this problem, and this is the biggest problem that I'm now working to resolve. Instead of using that, we have a character device, which we use I/O controls to control the GPIOs with. And this went on in kernel 4.8, I think. And since we have been trying to promote it. It's getting there. We have some certain ways to deal with it. Normally, you should not control GPIOs from user space. A lot of people do it, and those are the automation cases that I showed you on the first slide. You know, all automatic control and so on. Makers, builders, and so on. They want to control GPIOs from user space, and then they should use that, their dev GPIO ship N. And we have made some nice example tools, and there is the libgpiod that helps you to do this the right way. Since people are so infatuated with the old interface in SysFS, I decided to cleverly offer some goodies to make people automatically move over. So the first thing is, that thing is not even compiled into the kernel unless you ask for it. And I think Fedora, for the embedded world, has disabled it. So you have to use the second one. The second thing I did is all new features are added here only on the character device. So if you want to, for example, write several lines at a time or read several lines at a time to make a with a signal analyzer or something like that, yeah, the character device is there for you. I'm not going to add that to the old interface. I have deprecated this officially. Open drain. We don't have open drain over here, but there is open drain. So by just putting in more and more nice stuff over here, we are like pushing people in this direction. So it's a bit like politics. Yeah, so with this user space, you can read and write GPIO lines and so on. The second thing I'm going to talk about today is pin control, and we don't have a user space interface for that. And I'm not really sure that we should have. We should maybe have some of the pin configuration things for electrical properties, which I'm getting to, in user space. Maybe, maybe not. Depends on the use cases. Multiplexing, pin multiplexing, which is the other big thing that pin control is doing. As far as I can tell, it has no place in user space at all. No value to user space. But I have been wrong in the past. Yeah, I told everything about this slide. So the hardware looks something like this. Now we're going down in the silicon. What is pin control? What is GPIO? It's sort of the same hardware. The hardware usually looks something like this. This thing is an operational amplifier that you know from your education. Has somebody not seen an operational amplifier? Does everybody know what the totem pole output is? Yes, you do. Okay, good. Did anybody understand anything? This is a driver that drives this signal in an amplified manner out there. And here, from the same pad, you have an input thing with something called a Schmitt trigger that reads the same input back in. So since my laser pointer is not working, I'm going to use my fingers. this is called an I/O cell in ASIC design lingo. People who write silicon, who write ASICs, they have a set of libraries that they call cell libraries. And those libraries can contain a lot of things: gates, counters, entire blocks of buses, like an SPI block or something like that they just like jam into their design and build their chip around. It's a hierarchical thing. It goes from the lower to the higher, and at the bottom of it is usually these cell libraries. And the I/O cell is one specific cell library that deals with driving an input and output to the chip itself. I think I have a picture a little bit later in the presentation. Let's see if it's, yeah, it's there. Look here, here's the chip. There's the pad here, out on the ring. That's the thing that we're driving. And these here around the edges are the I/O cells. They are the transistors driving it. So that's that I/O pad. So you can see the signal coming in here, going out there, or coming in here and going in there into the system. Here we have the asynchronous edge detectors. Here we have multiplexers to connect different lines from the input and the output. We have pull down and pull up enable. Here are silicon resistors. They make them with depleted transistors, I think. This is usually all done in MOSFET technology these days. Some technology node. Usually for half analog chips, you use an older technology node with not as small microns. But in the newest ones, it's lying down in the nanometers. And I'm not showing you what's inside these boxes because it's complicated electronics. And frankly, everybody does it their own way. There are a number of people in this world who actually design these I/O cells. I have mailed with one of them. But I would like to meet them, but they are a handful of people. They work at companies like ST Microelectronics, TSMC, Texas Instruments, Philips, and they are like some special guys, because cell libraries is one of these competitive areas where all these silicon companies are really head-on competition with each other. So it's very hard to get to these people. We don't talk very much. We should, but what can I do? I don't know how to find them. And, oh, I'm doing this again. And as I said, here are the I/O cells. You put the chip in a package, something like that, something like that, something like that, and then you want to control the electricity, or the voltages, or current, or anything like that on these balls or pins or so on. So pin control is named after pins like that. It's not GPIO anymore. And this is one of the big misunderstandings that happen. GPIO is, for a software engineer, it's really that. Like, I'm a software engineer, so it's general purpose input-output. It's just some software register where I write and read something. For an ASIC engineer who writes these things, it's something else. They think it's a GPIO is this cell library thing, general purpose input-output that I take in my ASIC design tool from Mentor Graphics, and I synthesize something, and then I run it through a physical compiler for several hours, and out comes a floor plan, and I put the floor plan on the silicon, and that's GPIO for them. But that's not what it is from the Linux point of view. We just call it GPIO when it's actually general purpose from a software point of view, not from a hardware point of view. And that creates a big problem when it comes to data sheets, because data sheets are written by these people. So they just call it GPIO, but it's not GPIO. Sometimes it's GPIO. All right. Software-wise, we partition this I/O cell. I should have fixed this color. This is blue. This is gray, 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 gray. So let's say for a certain system, where we collect this as really GPIO. The gray things here are going into the GPIO subsystem. You see output enable, input enable, and that's all. And somewhere to read and write the lines. That's GPIO. But what about the rest? Pull down with the depleted transistors here. Pull up. Hysteresis control. You turn on this Schmitt trigger here. And the asynchronous and synchronous edge detectors. What do we do with them? Yeah, they go into other subsystems. So the pink stuff, that goes into pin control, and the blue stuff goes into the IRQ subsystem. So you find 3 different subsystems in the kernel that deal with this. There's GPIO, there's pin control, and there's IRQ chip. Pin config, we're going to talk about the pink stuff, pin configuration. What is that? What kind of electrical control can we do from software? Yeah, we can do a whole bunch of stuff, and it depends on how much the silicon engineer exposed to us in software. Sometimes a bit, sometimes very little. Usually pull up, pull down. It's these 2 things here. We can pull up the line, pull down the line, which is necessary if you're doing open drain, for example, and also for other reasons. We can drive the line in different ways if we're using it as an output. The driver stage is this one. In practice, it doesn't look like this. It looks more like that. The driver stage usually is more like this. I'm sorry for the bad illustration. It's from the Linux kernel. There's an inverted NMOS transistor right here and a PMOS transistor there, and that is called a totem pole. And that is this is a push-pull configuration if those switches are closed. If you don't close that switch, now let me think. If you open this switch, you get an open drain configuration on your totem pole, and if you open that switch instead, you get an open source. Not open source as in software, open source as in source. So you all know transistors, right? Good, thanks. And then sometimes inside this circuitry is a little timer, and then you have debouncing, and that means avoiding a lot of flicker from mechanical bouncing on the switches if you have a key, for example. You have a Schmitt trigger, as I showed you. That's another circuit that I don't show. Low power modes, power source selection. You can select different voltages on the chip to drive your output. Sleep state setup. If you're going to disarm the pad ring out there, usually there's a special sleep state to it. So this electronics, as you can see, it's in practice even more complicated than what I'm showing you. The I/O cells are really, really tricky. Slew rate, you can control and signal skew or delay. That's how the signals go in time over out and in of the chip. And state persistence. If you lose the setup of this line when you go to sleep with the entire system, or if it's persistent and persists over the sleep cycle. This kind of stuff, the system integrators and so on put into the chips. This is pretty tricky stuff. This open drain, for example, it's if you have open drain, you can drive a 12-volt line from a 3.3 volt chip. Even if the voltage on the chip is 3.3 volts. You do not use that. You put an external pull-up with a resistor up to 12 volt, and voila. Since it's open drain, you just put it into input mode when you want to drive it high. The pull-up resistor will pull it up to 12 volts, no problem. That's a popular way to use it. It became very electronic here. Is there a lot of software engineers in the class? I'm sorry, Hans. Well, he's an excellent electronics guy. He's just fooling you. Let's take one of those I/O cells and show you a little bit how the ASIC engineers, the programmers at making the chips are using it. I've talked for a long time already. All right. We take this one and we slam 8 of them after each other. Each of this input, output, output enable, input enable, those we connect to a register. We get 4 registers with 8 bits in each. It could be 16, could be 32. It depends on how many you want. All of a sudden you have, as a software engineer working with Linux, 4 times 8 bits that are called GPIO output enable, GPIO out value or data, input enable, input value. Sometimes the input and output value are in the same register, so it's like 3 registers. That's a very simple configuration, and it's appeared a lot in the past, so therefore we even have a library inside of GPIO subsystem to deal with it. It's called GPIO generic in kconfig, and the file is called gpio-mmio.c. You see that the ASIC engineer thought that this hysteresis control down here, they thought that's really boring, so he just hard-coded it to VDD and turned it on by default, and then he thought that, yeah, this stuff we're not using, so let's just ground it so they are disabled, the pull-up and the pull-downs. If you want pull-up and pull-downs, you have to put them outside the package with a physical resistor. So he just disabled some nice things that we would like to have under software control. But that's all right. ASIC engineers do that all the time, especially when they use that I/O cell for something else that is not generic purpose input-output, if it's a bus of some kind. For example, if it's I2C, then he will just enable this, because you have to have pull-ups on I2C bus lines, data clock. GPIO lib, when you look at the code, it looks something like that. This is part of the struct GPIO chip. Oh, nice. Showing code dumps in conference presentations is generally not such a good idea. But this is just to give you an idea about the callbacks we have here. We can give it a name. It has an internal device, has a parent, owner for the module, and then there's a bunch of callbacks here. There's a V table inside the chip for requesting, freeing, getting direction, setting output, input, getting the value, getting multiple values, setting multiple values, setting the configuration, which is kind of pin control, and to convert it to an interrupt number. And if you have that generic GPIO enabled, we also have some data that keeps track of which registers we use to just read and write. You can also implement that all by yourself, which is what a lot of drivers do, because different. Then, of course, we can take something more complicated. We get more bits in our registers. There are the 4 ones we saw before, but now we also have IRQ enable and something called falling. And then you sit there and scratch your head, what does this mean? Well, you always find exactly the same things in all data sheets. It's the same bits, the same things you configure. Yeah, it's just this thing with the synchronous edge detector over here. They don't have an asynchronous one, they just have a synchronous one. It needs a clock, probably. Probably there's some clock to the block that you have to enable from a clock controller, or the thing will not work. Sometimes you have to bring it out of reset as well. But it's just the same 1 bit per line. Enable here to turn on this IRQ out of the chip. And there's probably something like a big OR gate that just take the output from all of them and generate 1 input from all of them. And then there's a status register somewhere saying which one was it, if you're lucky. So you can see, you get an interrupt, which one was it, and then you created a cascaded interrupt chip. Now we have a library for that as well, generic IRQ chip. It looks like that. It's pretty complicated. Doing interrupts in the Linux kernel is a special chapter. Sometimes you want them to be chained, sometimes you want them to be threaded. As a superset, we refer to them as cascaded interrupts, that they are, you could think that the main interrupt controller in the system is the only interrupt controller, but that's not the case. Instead, you take one of the lines out here, and then you fan it out like that to all the lines on the GPIO, so it's also an interrupt chip. It's the same thing for the Linux kernel. We can have any number of them. Just as we can have many GPIO chips, we can have many interrupt controllers. One GPIO chip, one interrupt controller, or IRQ chip, as we call it, if it supports IRQ. Let's get really complex with the same IO cell. How much time do I have? Friends, help me. 12? 10? 10. Okay, it's fine. No problem. Let's make it really complex. Now we have multiplexers here. You can control with 2 bits, max 0 and max 1. And you can select input ABCD, output ABCD. We also have asynchronous edge detection, wake up enablement here, hysteresis, pull up, pull down, enable. Everything from our IO cell we expose to the software. This is still simple. I assure you, this is still simple. There are much harder things out there. We get all these registers, and since we have pin control, we have to kick in pin control and pin max and generic pin config to handle all of the business with the lines. Those 2 things up there go into some registers. How does that register look, where you control the multiplexing? Let's see. Okay, you can put it like that. So, yeah, that's the max line 0 from the first one, the second one, third one, and the max 0, and so on. What's the problem with that picture? Yeah, a lot of hardware engineers do this mistake, and we need to deal with it. If you write that register, this one has not changed yet. So your multiplex here goes through some intermediate state when you write this one and change that bit, and then you write that one and change that bit, and you get like a glitch. That's what happens. So many chips out there with this mistake in them. So if you just put it like that instead, like 2 lines like that, 2 lines like that, 2 lines like that, problem solved. Of course they get it wrong. So you find lots of interesting workarounds in the kernel for this glitch risk. And usually these days, what the engineers do is they put all the multiplexing in a single register, even if they just use 2 bits or 3 or something like that. Give it a whole register. There are plenty of registers. And then they're done with the problem. And they usually have the control 1 line at a time, just like I showed. But in the past, like engineers, they have apparently a lot of time on their hands, and they want to be really helpful to the software developers. So we have seen quite a lot of these kind of solutions, especially in the old ARM systems, that they give you a register where you tell a use case to the chip. Like, I want to use my ATA drive, or I want to use my PCI bus, or something like that. And then there's all kind of stuff going on here, which they have written in their VHDL, and out comes all of these max controls. And you can easily imagine if something, if there's a race in here, or something went wrong, what do? We do nothing. We spin a new ASIC. Not good. It's better to have it under software control. So these days, this kind of solutions is highly unrecommended. The pin control and GPIO subsystems are similar but different. So you saw very well how I partitioned the problem. Everything electrical and everything multiplexing is in pin control. Everything just driving and asserting and deasserting lines, that's in GPIO. And everything that deals with the IRQ is in the IRQ chip. And we just use all 3 at the same time. Sometimes it feels a bit construed. Sometimes I would be told, like, yeah, you should have totally just baked it into one subsystem, which is actually what I tried to do from the beginning. It was just too big. Instead, we have a mapping between pins and GPIOs. So a GPIO line is mapped to GPIO pin with something called a GPIO range. And And that way, the GPIO portion of a driver can cross-reference the pin control portion of a driver. A very good example of this is the Intel driver, which is written by Mika, I think, Westerberg, and a bit by Andy, and a bit by Johan, I think, Nyman, and a few others at Intel. But they actually decided to use everything exactly as designed. And I pushed them around a bit, and they have done an excellent job. So now you look at that driver, and you see, like, yeah, that's how you do it. You combine a GPIO chip, pin control, pin config, pin mux, all in one. There's also interrupts, of course. Everything. And just works. Yeah, you also have GPIO expanders and stuff coming in. And I had a slide of like some future things we should be working on. But I think if you have questions, it's better if we take them now. Did anybody understand anything? Yeah, okay, good.